Hello, my name is Nick DesChamps. I was president of DesChamps Laboratories from 1974 until 2007 when the Munters Corporation purchased DesChamps Laboratories. Presently, I'm a consultant to Munters. We've done a three-part series on history of indirect evaporative cooling at DesChamps and Munters that we'd like to show to you. And the first part is on the history of the development and use of the heat exchangers themselves and the problems that we faced. The second part of the series is on the development of the finite difference program that was required to produce the correct results for performance. And the third part is on the development of the heat exchangers, the polymer heat exchangers that we found were required to withstand the water spray on the heat exchangers. So the first part is going to be presented by Mike Scofield, founder of Conservation Mechanical Systems and a fellow in ASHRAE, and he has 40 years experience with indirect evaporative cooling. Now, he's being recorded on Skype. It's a new procedure for us. Its video quality is not quite as good as the other two parts to this procedure, but he did a good job. So here's Mike Scofield.
Hi, I'm Mike Scofield with Conservation Mechanical Systems, and I'm going to describe some of the history behind the early introduction of indirect or dry evaporative cooling in the Rocky Mountain area, specifically Denver, Colorado. Figure 2 shows an early Z-duct air-to-air heat exchanger that we used an atomizing nozzle at either the return air inlet to the heat exchanger or the scavenger outdoor air inlet. And we felt confident, although we had no tests to back it up at that time, that if we could cool the outdoor air or the return air down close to its wet bulb, we would achieve a great increase by working with the wet bulb instead of the building return air dry bulb. We would achieve a tremendous increase in sensible cooling of the outdoor air. At the time, we didn't realize some of the problems that come up when you atomize water and allow it to be sucked through a plate-type counterflow air-to-air heat exchanger. The dry-to-dry performance of this heat exchanger is roughly 60%, but by introducing this water, we felt at least that we could increase the performance on the makeup air side by the difference of the wet bulb condition on the wet side to the ambient summer dry bulb, which in Denver is around 93 degrees. So an interesting application came up in 1977, and the next figure shows a write-up that I obtained in the Daily Journal Dodge report on the Cherry Creek School District, which by code they had kitchen units and locker room units that required 100% outside air. Bill Kimball of McFall, Conkle and Kimball was the consultant engineer, and I went to Bill. Kind of an interesting story, and I didn't tell him we had test data. I said, "Look, it's pretty intuitive, Bill. If we spray water on the exhaust or scavenger air side of this 60% effective air-to-air heat exchanger, that will increase the sensible cooling effect." And I said, "Bill, I think I think you can reduce the tonnage by the chiller that serves these units, because each unit had a chill water coil. I said, I think you can shave about 50% of the tonnage off that chiller if you employ this concept. And I said, went on to say, Bill, I said, you know, you'd be a real pioneer in this industry, a real hero in the HVAC history book if you employed this and saved this much energy for your client. And he said, Mike, he said, I recognize all of the consultant engineers in our industry that are pioneers. He said, when they turn around, they're the ones with the arrows in their back. And therefore, we will have a chiller sized as if there wasn't even an air-to-air heat exchanger, let alone a wet air-to-air heat exchanger in this application. So they went ahead and installed the larger tonnage chiller, and lo and behold, the system worked. And we were able, it turns out, to keep that chiller, and it happened to be an air-cooled water chiller on the roof. We kept it off for a majority of the summer hours. So this system worked, and it worked very well. What we didn't know is what we were inviting downstream in terms of plating out of water hardness, and in the application of aggressive water eating up the heat exchanger, the aluminum, taking away material from the aluminum heat exchanger, which is worse actually than plating if you have aggressive water. And I always like to quote Adolf Coors. Brewery always talked about Rocky Mountain spring water and how it made a better beer, but it turns out that not all water being furnished, potable water being furnished in the Rocky Mountain area came from snow melt or Rocky Mountain spring. And we found out shortly that at very least we ought to coat the heat exchangers with a Davco 152 epoxy to prevent some of the aggressive water from eating the heat exchanger up. So the next project that we got involved in is the project in Sheridan, Wyoming, which was a capital savings job site. And there we, I think, used, once again, the atomizing sprays. And if you look at the photograph, Gary Griffith is holding his hand on the spray manifold. And so we were still, even at that time, which was 1979, a year later, a couple of years later, we were still using the sprayed heat exchanger. And we didn't go to a spray at the top with air coming down to achieve a better wetting until some years later. But in any case, we learned our lesson in using a water spray on aluminum, and the lesson was that it definitely shortened the life expectancy of the indirect evap cooling heat exchanger. The first brochure that describes this concept, as far as we know, in the United States was shown on the next page there, and is the heat exchanger using the Series 79 same counterflow 1000 CFM modules, but coupled together in a larger manifolded heat exchanger section that allowed us to treat larger CFMs. So kind of going to the issues of spraying aluminum plate heat exchangers and wrapping it up, in addition to the fact that wetting a heat exchanger is very exciting, to say the least, with water of of a certain hardness or water that is aggressive or corrosive. We found out that there is also a leakage problem. The sealing of the plates in our heat exchanger was quite good, but still we would get on occasion leakage from the wet side of the heat exchanger to the dry side. And if the leaking got really bad, what the owner pointed out was instead of an indirect or dry evaporative cooler, he had instead purchased a very expensive direct evap cooler because both sides were getting wet due to air leakage. So we needed to find a solution to air and water cross-contamination between the wet side and the dry side. I think that the new polymer tube heat exchangers, which the beta site for the EPX technology was in 1997. I believe we sold the first of these to the Warwick Hospital project, and that project was a surgery. And interestingly enough, the unit that we furnished replaced a Vericool unit, which was another attempt at indirect evap cooling, used round tubes with a wick. And the problem that they had with water hardness limited their use. So we were replacing the Vericool indirect cooling heat exchanger with the Munters EPX, but with vertical tubes. Interesting to note that heat exchanger is still quite clean and in service from 1997, and that heat exchanger is at the Santa Rosa Warwick Hospital in Santa Rosa, California. Anytime you have a surgery or a hospital application, typically in California, and I think it's the case throughout the United States, we need 100% outside air for surgery. This system is an excellent application of dry evaporative cooling and has a tremendous impact now in California, because with a 70% wet bulb depression efficiency, which is the approach of the wet side wet bulb to, or I should say, the approach of the ambient outdoor air dry bulb to the wet side wet bulb. In California, this can result in a tremendous reduction in sensible cooling load, roughly 40 to 50% in the Sacramento Valley area. And we're using these now actually, and compared to a more conventional 30% or 25% outside air economizer, we can reduce peak building cooling demand by 30 to 50% in California compared to a more conventional air side economizer introducing in only 25% outside air. So we've taken it the next step with the polymer tube. We've taken the design from a vertical to a horizontal application, where we have found that the ability of the tubes flexing during fan startup causes a self-cleaning of the heat exchanger surface and the removal of water hardness from the wet side surface after the buildup gets to a certain mill thickness. The tubes flexing, shaking during fan startup successfully shed the surface and allow the heat exchanger to work at as new effectiveness. So, as you know, we've applied these systems now also to data centers where ASHRAE TC 9.9 requirements are reliability of 99.59s, and so we're using them to reject the heat from hot aisles in data centers to the ambient wet bulb and recirculating that air then back to the inlet to the cold aisle. The reduction in the performance, the reduction in energy requirements are tremendous because this heat rejection is accomplished roughly at 0.2 kW per ton or less. And comparing that to an air-cooled water chiller or an air-cooled DX system, where the heat is extracted and then through refrigeration rejected to the atmosphere, the kW per ton is usually around 1 or 1.2. So tremendous increase in energy efficiency of these systems in data center applications. One of the reasons that the horizontal arrangement of these tubes was selected is that we increased the wetted surface of the heat exchanger, and the airfoil shape on the wet side reduced the parasitic loss. Since many of these heat exchangers, like data centers, will use a constant flow by reducing the wet side static pressure penalty, we reduce the parasitic losses attributed to the cooling system. So these figures that show the shedding of that onion skin, and I think we refer to it as water hardness buildup on the wet side of the tube, pretty much visually tells the story of what's going on inside that heat exchanger, allowing the system to maintain full effectiveness even after years and years of service. I think this is the tremendous breakthrough. As you know, Nick and I sold a couple of these units into Death Valley at the Cow Creek Maintenance Facility. And don't know if you know how much, what the water hardness is in Death Valley, but it comes out of the tap pretty much at 1,500 parts per million, which I like to compare to liquid rock. So we've had these systems installed now since 2006. And Nick's been back to take photographs, and they're still in operation. And Wayne Batter, the facilities maintenance guy, says the only complaints they get is on 130-degree ambient condition in Death Valley. It's sometimes too cool in the maintenance facility, which was music to our ears. Anyway, that winds up my section of the presentation. I appreciate your time. Thank you for listening in.